Hey everybody, today's lesson is on solving systems of inequalities by graphing. A few things to remember about graphing inequalities that we've covered in previous sections. The boundary line of the solution region is found by graphing the related equations. You can take an inequality and think about changing the less than or greater than symbol to an equal sign and graphing however you would normally graph the related equation. If it's a less than or a greater than symbol, you're going to use a dashed line for the boundary. And if it's a greater than or equal to or less than or equal to symbol, you're going to use a solid line for the boundary. Deciding where to shade, there's a couple of different ways to do that depending on the type of equation you're graphing, but a way that will always work is to pick a point in the region, in either of the regions, and test it into the original equation to see if it works. If it works, that means that it is in the solution region and you should shade that region. If it doesn't work, then that would be not included in the solution, so you should not shade that region. In this section, we're going to look at systems of inequalities, and remember that systems just mean one or more at a time. So we're going to look at two or more at a time, and we're going to think about shading the region that overlaps. Let's take a look at this example. Our goal is to solve by graphing. Our first equation is x squared plus y squared is less than or equal to 49. Well, if I think about the related equation, I know that this is the equation of a circle whose center is 0, 0. And the radius, remember this represents r squared, so the radius is 7. I'm going to go ahead and graph that. We have a center of 0, 0, and radius is 7. So here's a point at 7, here, 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 and here. And then we have to decide, should it be a solid or a dashed line? Well, it's less than or equal to. It could be equal to the boundary line. So I'm going to go ahead and draw in a solid line to connect the points. Now I have to decide, am I going to shade inside the circle or am I going to shade outside the circle? Well, if we think about the meaning of this symbol, this x squared plus y squared is less than or equal to 49, less than or equal to a radius 7. Well, less than or equal to radius 7 would be everything inside. So we can think about, I'm going to very, very lightly shade inside the circle. We can also make sure that this is the correct region by testing a point in the region. 0, 0 is a really simple point in the region. So let's test 0, 0. If we plug that in, 0 squared plus 0 squared, is that less than or equal to 49? Yes, it checks out, so that means the inside of the circle is the solution region. Now let's think about graphing the second equation. We have x squared minus 4y squared. As soon as I notice that the x squared and the y squared terms are opposite signs, I know it's a hyperbola. And to graph a hyperbola in standard form, we always want to get 1 on the other side of the equation. So I'm going to start by dividing each term by 16. X squared over 16. If I simplify here, minus y squared over 4 is greater than 1. All right, well, this is a hyperbola. Again, the center is 0, 0. And I know that in the x direction, I'm going to travel 4 because 16 is 4 squared. So we can go 1, 2, 3, 4. And 4 in the x direction over this way. I'm using open circles because it's greater than it cannot be equal to. In the y direction, 4 is the same as 2 squared, so we're going to go 2 in either direction. And those 4 points create our fundamental rectangle that's going to be used to graph our hyperbola. The asymptotes will also go through the corners of that fundamental rectangle and through the center. Since the x squared is the positive term, I know that the vertices are these points here in the x direction, and I'm going to use a dotted line to graph my hyperbola. All right, and then again, we can think about greater than 1. If it's greater than the graph of the hyperbola, it's probably going to be outside. So I'm thinking we're going to be shading outside the hyperbola here and here. But again, we can always test a point. A point that would be outside of the hyperbola looks like we could choose maybe like this point right here, 6, 0, or I mean, any point would work. You could plug in like 10, 3. But choosing one with a 0 makes it a little bit easier. So I'm going to test the point 6, 0. And if we plug that in, we get 6 squared over 16 minus 0 squared over 4. Is that greater than 1? Well, this term becomes 0. 6 squared is 36. 36 divided by 16, is that greater than 1? Yes. So if it was just the hyperbola, this would be part of the solution region outside here. And we would shade all of this outside here. But our final answer is where both of those shaded regions overlap. So where are we shading inside the circle and outside the parabola? It's just this region right here and this region right here. This dark shaded region is the solution to the system of inequalities. Every point that lies within these two little regions are solutions to both of these equations. Let's take a look at one more example. In example 2, we have two equations. The first one, I know just by looking at it, we have an x squared and a y squared term. They have the same coefficient, so this is going to be a circle. And